we thank thee for this day. We thank thee for some of the things that we were able to have done in this program so far. And please bless that the Spirit may be present as we study these things together. And we see these things in the name of Jesus Christ.
Amen. All right, so we're on day 2 of the momentum equation, working our way through the full transport equations. I was working on my notes for energy equation last night and this morning. There's a bunch of algebra in there. I was trying to figure out how we could not do all that algebra in class. We'll have to gotta figure that out still. I had like 10 pages. I was like, all right, that's definitely not gonna work for class. So we'll see what I can figure out by Friday when we start that guy. But so today, hopefully we'll finish up momentum equation. We've got, we did this part, so I guess I've been putting a little arrow. So we got to here last time. Okay, so now we're starting on this part, solving Navier-Stokes. Were there any, as you reflected or started working on your homework, were there questions from part 1 that you wanted to ask? Maybe I'll just pause real quick and make sure that we're good. We're good on this. So here, just to review maybe real quick, we talked about a momentum balance and we got the Cauchy momentum equation, right? And we said, well, that equation's great, except that we can't solve it because there's way more unknowns than there are equations. There were only 3 equations. So we said we needed to go looking for more. So the first thing we did was we put in Newton's law of viscosity. That helped out a lot, right? And then we still had one more unknown than equations. So we did the continuity equation that gave us a mass balance constraint on our velocities. So that coupled set, we then got the Navier-Stokes equation. Then we took a little detour and said, let's think about that in an Eulerian versus Lagrangian perspective. Eulerian's this fixed frame while you're watching the world flow by. Lagrangian, you're in the fluid following it around. And we saw that the material derivative was indicative of the Lagrangian frame of reference, right? And so we can think about the Navier-Stokes equation as either this thing fixed on the sideline where there's stuff flowing in and out of a box, or we can think about it as if we're moving along with the fluid and it's a material element that is experiencing forces, right? So there's sort of 2 interpretations of that equation, and one we write the material derivative of that. So now let's talk about solving. Okay, and we'll start to think about that. So the first thing to note, and I think we said this last time, is that we don't have a general solution, right? So if we write up the Navier-Stokes equations again, just to remind ourselves, we have rho dv dt is equal to minus grad p plus mu grad squared of v plus rho g. And then we have also along with that the continuity equation del dot v is equal to 0. Okay. Remember the assumptions here was constant density, so an incompressible system, and Newtonian fluid, so constant mu. So this has constant rho n. Okay, so we said that there's no general solution. I guess no known general solution. Okay, if you'd like to discover one, that would be great. Okay, I'd appreciate it. Probably get a Nobel Prize while you're at it. That would be awesome. So let's think about what makes these equations hard. All right. So these are a set of. This is a nonlinear PDE. Okay, it's nonlinear because in here there's a v dot grad v term, right? So that's nonlinear term. Vx is multiplied by gradients, okay? That's nonlinear. It's actually a system, right? So there's 4 equations, so they're coupled. So that always makes our life a little harder. You think about that maybe in reactors, right? Maybe you have done these rate equations, and you can do one, but then if you have to do like 5 of them together, that gets harder, right? And so there's 4 equations here that are coupled. And this actually has, it's constrained. So we haven't talked a lot about that, but we kind of mentioned it when we said that mass conservation acts as a constraint. So you can see we don't have explicit equation for the pressure, right? We have equations for, the momentum here, which we can think of as equations for the velocities, but we have no equation for the pressure. And this is setting a constraint on the velocity field. So you can think about this like a Lagrange multiplier problem. Turns out the Lagrange multiplier in this case is actually the pressure. So like you ever remember this from your calculus class, probably multivariable calculus class, where you had like some function and you said, I'm going to constrain it to this surface, and then you added plus lambda times this constraint, okay? And then you minimized that problem. I'm seeing just blank stares. So did you ever do Lagrange multipliers? Probably. Okay, so that's a thing maybe just go back and look at because we're talking about it today, okay? But this is effectively a Lagrange multiplier constraint to this PDE, okay? So instead of thinking of this as like 4 equations and 4 unknowns, you can really think of this as 3 equations with a constraint. The multiplier is P. That would be your lambda, okay? So the pressure actually kind of changes meaning when an incompressible system. So in a fully compressible system, the pressure and density and temperature are all related by some equation of state, okay? But we've said the density is constant. That's an equation of state assumption in a way. And now the pressure is decoupled from that density. So the pressure actually is no longer the thermodynamic pressure. It's this constraint. It's this Lagrange multiplier here. Sometimes we call this pressure the mechanical pressure. Okay, so it has the same meaning as like stress, okay, but it doesn't end up mattering in thermodynamics in the same way. So we have to be a little careful with that. We'll see that, we'll talk a little bit more about the thermo when we do the energy equation. Okay, so this is just some stuff to be aware of. It won't probably matter a whole lot in mathematically like solving out, but these are some subtleties that maybe you need to start to get familiar with sort of at this graduate level, okay? And then, when we say PDE here, I guess maybe I won't put a comma, it depends on both space and time. Okay, so space we have boundary value problems, time we have initial value problems. So in general, this is, what would they call it? Initial boundary value problem by BVP. Okay, so it's like, it's all of the hard things, right? Like it's not like just any one of these things could be kind of hard to deal with, right? Like if we had a linear, ODE that was constrained, that's kind of hard. That's like what you're doing in controls problem. Okay, they often add constraints, right? If it was a nonlinear PDE, that's hard. But like it's all of the stuff. Okay, like all the hard things you can think of, it's in there. So that's kind of a bummer. So what we'd like to do then is simplify it, right? We'd like to find simplifications of Navier-Stokes so we don't have to solve this whole hard problem. Turns out if we want to just go at this guy, we can start numerical solutions, and we'll probably talk about that at least a day in the class. I saw that in the outline in the future, so we'll see how much we talk about that and how much we talk about CFD. Okay, but there's a whole field of computational fluid dynamics, okay, that you're interested in, right? Which is about how do we solve this on a computer, right? But before we get there, we'd like to understand maybe some of the limits of what we can get out analytically. That'll help us, if nothing else, make sure that our computer solutions are right, okay? And also, it's a lot better if we have something analytical, right? We can then couple that to an energy equation or other equation, right? And solve those cases. So we don't always want to have to rely on computers if we don't have to. So what we're going to do is we're going to start out with dimensional analysis. Okay, and in the dimensional analysis, we're going to try and use that to rationalize some simplifications. Okay, sometimes I think you've probably seen these before. In fluids, I did the dimensional analysis too, so hopefully this isn't completely new. But for me, I'd never seen a dimensional analysis before I went to grad school. And I saw these simplifications and it was always really confusing. And to me, the dimensional analysis helps you see where the approximations sort of fit in a broader framework so that you can understand when they're good and when they're not good. So that's what we're going to try and use to motivate this. Okay? So the first thing before we do that is a little quick thing to help us write this a little more simply. And that's to introduce the dynamic pressure. I think we maybe have seen this before. But the dynamic pressure is this curly P. And then we write it as P plus rho GH. Okay? And H is this sort of height, right? This is the fluid statics term. And it depends on what coordinate system you set what H is. Oftentimes it's the exact same thing as Z, right? If you set the 0, you know, at the Z-axis, but sometimes it's not. You might have Z going in the negative direction. So they use an H in BSL to sort of indicate that it's always the height, whereas Z can be down or up or whatever, okay? So in our case, we'll just assume it's rho GZ for now, because that makes our life easier. And if we take the gradient of this guy, we take grad curly P, we get grad P plus grad rho GZ, which is grad P, and then I'm going to call that minus rho G. And the reason I say it's minus rho G is because I'm calling the G vector 0, 0, minus G. Okay, if you remember, that was the definition of the G vector that we've used in the past. Okay, so then the minus sign cancels with that minus sign, and we get that guy. Okay, so what's useful here is we now have minus grad P plus rho G. So here we have grad P minus rho G. So minus grad P is equal to the same as that. So we can, you know, take that guy away and that guy away and just write a minus grad curly P. Okay, and that makes our life easier. So we can rewrite Navier-Stokes as, let's see, rho dV dt equal to minus grad curly P plus mu grad squared V del dot V equals 0. Okay, so thinking about that, it's the shortest way I know to write the Navier-Stokes equation, right? We only have to write out 3 different terms. Okay, and units all work out, and we're going to use that one for our dimensional analysis. Okay, so if you remember, in dimensional analysis, we need characteristic scales. Okay, one way to think about dimensional analysis is we're like redefining units to be the units of the problem as opposed to the whatever units that they decided, right? So you could have it kilograms, but that's just some weight, right? Okay, or we have it pounds, but who knows where pounds come from? Even weirder British definition, right? So, you know, we need some scale of the problem, okay? And then we need a scale for our fundamental units. So the fundamental units in mechanics are length, time, and either a stress or an energy. So here it's easiest to do a stress. But stress and energy are the same, right? I mean, they're not exactly the same unit, but if you take stress multiplied by what, length cubed, you get energy, right? So we have length. If we define a length, then we have a stress. We also have an energy scale we define. Okay, so the question is, where do we get these characteristic scales from? Like, what do we, when we're thinking mathematically, where are we going to get them from? What do you think? Where are these scales going to come from? Any thoughts about that? You understand what I mean? Like, I'm just trying to connect a little bit with you because it's, I'm already 15 minutes into talking. We're all sitting here. So if you're confused by the question, say that too. That's perfectly fine. What do you think, Mark? I'm picking on you.
The question is, where do these scales come from?
Yeah, where are we going to come up with these scales?
Things in the problem, like a diameter, pressure.
Yeah, so that's a great, right. So like if we had like a pipe, right? We would have the pipe diameter, right? Great answer. Okay, so where would that come in the math? So remember when we did these balance problems, right? Where does this geometry come in the math? What do you think, Brian?
Not quite sure what you mean for that.
So when I did the shell balance problems, we would have a differential equation and then it turned into a boundary value problem, right? And somewhere in there, we would have things like a pipe diameter. Do you remember where?
Did that come from volume terms?
Okay, we had volume terms. You're remembering the shell balance derivation. But I'm thinking, like, think about when we did the pipe flow problem. Okay, and in the pipe flow problem, right, like if we're thinking about this one, we had the shell balance already, and then we wanted to solve it, right? So what were the steps? We did the 2 integrations, right? And then we got out these constants, and we need to evaluate the constants from the boundary conditions. So where in that step did the geometry matter?
Was it the boundary
It
condition?
was the boundary conditions, right? Because when we evaluate the boundary conditions, you have to say like, at the wall, there's no slip, right? Or at the wall, there's, or in the middle, it's reflective or whatever, right? So these scales usually come from the boundary conditions. Does that make sense, Brian?
Yeah.
Okay, so, usually if you're like struggling in a problem to find the length scale or the time scale, go look at the boundary conditions and see what they are. Okay, so let's just use one. We'll pick a problem as an example to kind of motivate us. So let's pick the example of the parallel plate simple shear problem that we'd like always pick. Okay, so in this one, remember we've got velocity profile like this. When that top plate moves U, okay, and we're going to pick L to be the length scale of the gap between those. So if I do that, I have a length scale already, right? My length scale is L. It's that gap length, okay? And the time scale, well, this is a velocity. A velocity is a length per time, right? And then I have a length, so I can combine those two scales and get a time scale. So the time is going to be a length per velocity, right? Because that should give me, 1 over time in the bottom, which gives me the time. Okay, so now I have those two scales. So the last thing I need is a stress or a pressure scale. Okay, so how am I going to come up with a pressure scale? So now so some of you had me in fluids, and we talked about characteristic scales of fluids. And I told you that we had things like rho u squared and u over L. Do these look familiar? Any of you? Okay, you're having nightmares about my first exam. Okay, so this is just a combination of these lengths and velocity scales. Okay, where if I pick them and I use some constants in the problem already, rho and mu, can I get a stress out? Okay, but, that's one way to think about it. And this, if you look at it, this is like mv squared. So that's like kinetic energy. Okay, so this is called the inertial scale. Okay, and this one has a viscosity in it. It looks like Newton's law of viscosity, actually. If you remember, Newton's law of viscosity was mu times dvx dy, right? And that's what that is. That has a u divided by L. Okay, so this is the viscous stress scale. Okay, so now I have to pick what my stress scale is going to be, and I don't know which one of those it's going to be. All right, I could just pick one and go ahead, but I'm going to Just say it's the sum of both of them. Why not? Okay? So I'm going to say it's rho u squared plus mu u over L. Okay? And that just makes my life easier. It turns out, as you probably remember from fluids, right, that when speeds are fast, the inertial stress scale is going to dominate. And when speeds are slow, this scale will dominate. Both will be in that Navier-Stokes equation, so I'm just going to make it the sum. And sometimes one will be big and sometimes the other will be big. Okay? All right. So, erase. Questions while I'm erasing?
I'm a little confused why we need the characteristic scales, but maybe that will become clear as we move forward.
Okay, great question. We're going to do it right now. So what we're going to do is rescale our variables in the problem using these characteristic scales. So I'm going to say that time, for instance, a dimensionless time, is time divided by my time scale, which is an L over U. Okay, and then I can define a characteristic, or I can define my x, y, and z, okay, and that's going to be x divided by L. And if I have a velocity, I'm going to need my time and length scale, but that'll combine to just give me back u, okay, hopefully. So I'm going to have v over u. What else do I need? Other variables I have in here, okay, I have a gradient. A gradient has units of 1 over length, right? Because it's a d dx, so there's an x in the denominator. So that one I'm going to multiply by a length scale. Give me a dimensionless thing. I could also think about that just taking this x and plugging it in. I'm going to get L's that come out in the numerator. And I need dimensionless dynamic pressure. And I divide that by rho u squared plus mu u over L. Okay? So these are just these are new variables I define. I'm rescaling them, right? They were in kilograms, you know, let's say that, or let's say it's in meters. Length was also in meters. So when I divide by that, this has no meter units. And we can think about this as being in L units, right? This is in how many L's do I have, right? So if that's gap height, you know, it's how many gap height is that X? Well, it's going to be something between 0 and 1, presumably in the problem, right? So we've now picked a new set of units for our problem. So now how do we manipulate this into the Navier-Stokes equation? Well, here we have an equation in our old units. We solve these guys for the dimensional units and then substitute them in. So I just invert all these relationships, right? So this one tells me that T is T tilde times L over U. This one says that X is X tilde times L. This tells me that V is equal to V tilde times U. This one tells me that gradients are equal to gradients times 1 over L. And this one says that the dynamic pressure is the dimensionless dynamic pressure multiplied by rho u squared plus mu u over L. Okay? And then once I have these, I take and substitute them back in to the Navier-Stokes equation. So I can do that right here. So I have rho, and then d, and then T has a T tilde L over U, and V is a V tilde U, is equal to minus the gradient should be 1 over L gradient tilde, and then inside P becomes P tilde multiplied by rho u squared plus mu u over L. Square bracket on that one. Plus, and then I have mu del squared. That should just give me a square there, right? So I have a divided by L squared, gradient squared. And then V add V tilde U. Okay? Does that make sense? You think, Mark? Good? We're good? Okay. We can also do this with del dot V equals 0, but it's kind of pointless, okay? Because this is going to have an L and that's going to have a U and they're going to cancel out and we'll just get the dimensionless del dot V equals 0. So that one's super easy. So we can just write that one up real quick. Del dot V, oops, equals 0. That becomes 1 over L dot V U equals 0. Okay. So in both of these cases, now what we're going to do is all of these things inside the derivatives, they're constant, right? So they can come out of the derivatives, and we're going to aggregate them and then rearrange, divide until we get dimensionless equations. Okay. So this one I just said, that's easy. This is going to give us del dot V equals 0. Okay. Well, let's look at this one. Let's collect the terms. I have rho U divided by, in the bottom I have L, then I have another U that comes up to the top. So rho U squared over L, dV tilde dt tilde is equal to, all right, and then this one, that chunk comes out. So I get rho U squared over L plus mu U over L squared. Grad dynamic P. I forgot the minus sign. Plus, and then this one gets a mu U over L squared, grad squared E tilde. Okay. So now, if I want to make the equation dimensionless, right, all the units are inside these prefactors. So I just have to divide by the prefactor. The easiest one to divide by is right here, in front of the dV dt. So I multiply both sides by L over rho U squared. So then I get dV dt tilde. Rho U over L squared, that gives me a minus 1 right there, right? And then I have mu U over L squared, and over here is rho U squared L. I'll leave that one alone for a second. Grad dynamic P plus, and I'll do this guy, it'll be the same product as this one. U over L squared, L over rho U squared, grad squared. That looks like it's the same. Okay. I'll erase this little. Okay, so now I just need to do this product. Let's look at what that is. I have mu U over L squared multiplied by L over rho U squared. Well, the L and the L squared, that's easy. That cancels. I get a U cancels there. So that, just to rewrite that to be a little clean, I get mu over L rho U. We should recognize that one. What is that? Anybody?
The inverse of the Reynolds.
It's the inverse of the Reynolds number. 1 over the Reynolds number. Okay, so this guy I can rewrite as V T is equal to minus 1 plus Reynolds, 1 over the Reynolds number. I'll put a minus 1. Save myself. Grad dynamic P plus, we'll do Reynolds number minus 1, grad squared, tilde squared, V tilde. Okay? That's the dimensionless Navier-Stokes equation. Where do we get to? Yes.
Your the piece after the grad tail, that's a
Dynamic
pressure, not a row.
Yeah. My rows look like that, silly. My dynamic piece, they kind of look the same. That's all I can do.
Just check.
I can't type stuff with my hands. Anyway. Yeah, writing equations is kind of hard, but that's right. We can try and make that more curly. Let's see what we can do. Kind of curly P. Is that a little better? A little more script-like. How do yours look?
Oh, not that great.
You gotta practice a little. We're gonna have to do this on our homework. Practice a little curly P's. Okay, so that's the dimensionless Navier-Stokes. The part B here is I'm gonna talk about how this is useful. Okay, but do you understand the process of how we got here? Make sense? Roya, you good? B is 3.
This is specifically for the two plate situation.
This is for any situation where I have a characteristic length and a characteristic velocity scale. So the two plate situation is one of those, but I also have one of those in pipe flow. I can rewrite that in the same way, and many other cases. So it's actually more general than that, but
He's not dimensionalized.
that was a way to think about it, right? That worked. Good question. I like those kind of questions. You just pull the wool over our eyes. What did you do, Doctor? Okay. So why all this work to non-dimensionalize Navier-Stokes, right? We still have Navier-Stokes. This seems like a pain. What's the use? Okay. So let's think of some useful simplifications of this equation that might help us solve. Okay. So the first one is, suppose that the Reynolds number is much greater than 1. Really big. Okay, another way to think about that. Suppose the Reynolds number goes to infinity. A really, really big Reynolds number. Okay, what does that mean? Well, we said that if rho u squared is going to be much, much greater than mu u over L. Notice that that's what we had in this ratio here, was the ratio of those two scales. So when the Reynolds number is much bigger than 1, then we can simplify this equation. So this part is going to go away, right? Because Reynolds number is big, so that number is small. That part will go away. So we get dv dt is equal to minus grad dynamic. Okay? So we can rewrite that. I'm not going to take the time, but you can undo the non-dimensionalization and get back dimensional units. And it'll look like rho dv dt is equal to minus grad p plus rho g. Okay? And there's a del dot v equals 0 as well. Okay? These two guys together, this is called Euler's equation. All right. So maybe you remember from fluid mechanics, maybe you can tell from here. What is characteristic of Euler's equation? What physically is going on? What term did we get rid of? Maybe that's not the question. What term went away? Christina, what do you think? Which term dropped out from Navier-Stokes? There were 3 terms, right? This term, this term, this term. Which one went away?
Grad squared v.
Grad squared v. That's right. Okay, so what does grad squared v mean in Navier-Stokes equation? What's usually in front of it, right? In the dimensional. Look at your notes. What is in front of the grad squared v? Viscosity. Viscosity, right? So do you remember we got that one from the divergence of the viscous stress? It was del dot tau, and that became grad squared v, or eventually, right? So that's the viscous stresses. So what we just said was that a high Reynolds number, viscous stresses aren't important anymore. Viscosity is not important. That makes sense, okay? We just said inertia is bigger than viscous stresses, okay? So the Euler's equation is when we can basically neglect viscosity, right? So that also makes sense. The Reynolds number is really big when viscosity is really little, okay? There's all those different ways to kind of think about it. So, you know, that's when Euler's equation. So this is good. The Euler's equation is good for big things going fast in low viscosity fluids, airplanes, okay? Big boats, things like that, okay? Your car, okay? So what happens here, because we lost the viscous term, that made our equation ideal in some sense, right? Viscosity is responsible for entropy generation, right? There's friction. So we lost that, so there's some kind of ideal, you know, conservation of something, okay? And we'll see about that later. So this ends up giving us, I'll say, a kind of ideal flow, okay? What we'll see is that if it's irrotational, we'll get out what's called potential flow, all right? And we'll be able to look at it kind of like a electricity magnetism problem, all right? Where you have these lines of potential that are between different things, okay? So this is one useful simplification. So it's also inviscid flow, okay? No friction. Does that make sense, right? That that's a useful simplification. Like you can think about that just if you think about taking a mechanics class and I took friction out of the problem, right? That made the problem easier in some way. So that's kind of what we've done. We've taken friction. Okay, here's another limit. Suppose that the Reynolds number is much less than 1. Or another way to think about that is that the Reynolds number goes to 0. Okay, now what happens to these guys? Well, that's a little hard to imagine because if Reynolds number goes to 0, that blows up to infinity, right? That one blows up to infinity. Let's multiply it across the board by the Reynolds number. That'll help us out. So if I multiply both sides by the Reynolds number, I get Reynolds number dV dt, and then I get a minus Reynolds number plus 1 grad P plus grad squared V. So many lines and fills and hooks and whatever, right? Man, it taxes your right. Okay, so what's going on here? So now I can take the Reynolds number to 0, right? Nothing blows up to infinity here. When I do that, this guy goes away, and then this guy goes away. And I get 0 equals minus grad dynamic P plus grad squared V tilde. There, that's what I want. Okay, so there I lost the time-dependent term, and I lost, I guess that's really all I lost, right? Was the time-dependent. Okay, so what is this term? Where does that term come from in our moment of balance? What is that one about? What do you think, Gloria? This term here, the material derivative term. What does that one represent? What does it mean physically?
The velocity of
So think about that. I have a derivative of a velocity with respect to time. So think about, like, there's a couple different ways to think about it. So one is just, what is a derivative of velocity with respect to time? Think freshman calculus. If I just take dv dt, what's dv dt? For freshman physics. Acceleration. Acceleration, right? Okay. So I took away all acceleration, right? So we also had said, we had like the force is the force, or the mass times acceleration is the sum of the forces, right? So we just took away mass times acceleration over here, set it equal to 0. So we said the sum of forces is equal to 0. That's like statics in some sense, right? Like if there's not a force, something's not moving, okay? So we have a fluid that's so sticky that it's over-damped, right? But I have to keep pushing it. As soon as I stop pushing it, nothing moves anymore, okay? So think like what happens if you tried to swim in, like in corn syrup, right? Like you're trying to swim, you almost have no momentum that sort of carries you forward, right? You're just sitting there. You have to push yourself forward to be able to move, okay? So this one is called creeping flow. Okay, then it has, no acceleration. Okay, if I write this in dimensional units, I get 0 is equal to minus grad p plus mu grad squared v. Okay, so in dimensional units, you just get the mu back. Okay, so what makes this one easier, is that this is linear. Okay. So I got rid of this acceleration term. Remember, it had this v dot grad v in it. So there's all sorts of stuff we can do to solve linear equations. It's still got the grad p in it. So there's still a constraint, right? I still have the del dot v equals 0. But it's sure a heck of a lot easier than the full Navier-Stokes equation. Okay, so those are 2 simplifications. Let's talk about the third. There's questions on these. Euler's creeping flow. I guess I put a box around that. I don't want to give creeping flow. It's not, it's 2. It's the one I do. So like big things going fast, Euler's equation. Small things going slow, creeping flow. So airplanes and cells. Okay, so if you're biophysics, okay, and you ever have to do fluid mechanics, you're doing creeping flow. Okay, you can think about that. Sit down one time and think about the length and time scales for a cell, and plug them in the Reynolds number. What Reynolds number are you going to get out? It's like 10 to the minus 3 or 5 or something, right? Definitely creeping flow. Or colloids, or polymers most of the time, or what other things are small? Oil inside rock formations, if you're a petroleum engineer. Lots of chemical engineering flows happen at low Reynolds number. Dr. Lignell's like the only fluid dynamicist, not only, but like his area is the only area in chemical engineering where I know that they really care about high Reynolds number flow. A lot of the chemies that I know are more into low Reynolds number flow and then rheology. What happens when it's a non-returning fluid? That's a lot of chemical fluid mechanics. Okay, so this is 3. I guess I didn't put like 1, 2, 3. I said 3 simplifications. This one's 1. This one's 2. Okay, 3 is it's kind of a little bit of a different one. Okay, it's unidirectional flow. Okay. In unidirectional flow, these are a subset of laminar flows. And in this case, you assume that the velocity has only one direction. Okay, so you say, in Cartesian coordinates, for example, velocity is all in the x direction. Okay, and this this assumption greatly simplifies the Navier-Stokes equation. All right, so if you put this in just in Cartesian coordinates, if you think about this for a minute, if you put this in the continuity equation, you're going to have dvx dx plus dvy dy plus dvz dz equals 0. Okay, so if you know that vy and vz are both 0, then immediately you can say that dvx dx equals 0. Okay, so that's just conservation of mass. So that says if all my flow is in one direction, then as I go along in that direction, the velocity can't be changing. I can't be like all of a sudden adding mass or taking mass away. Velocity has to continue on in that direction. So unidirectional assumption, so this is unidirectional, okay, leads to this assumption, which is, no, just blank, no, it's fully developed. Okay, so you probably saw this in pipe flow when you talked about this in chemical engineering, fluid mechanics, right? You did pipe flow and you said the flow profile is the same here as it is, you know, down the pipe here, it's fully developed, okay? And so unidirectional flows have to be fully developed. The other thing, if we look at the convection or the nonlinear term, okay, if we look at the convection term, that's this guy, V dot grad V. That's the one that makes our life hard that we got rid of in previous flow. We assume unidirectional. Let me write this out in index notation. This is VI del I Vj. Okay, but if I have unidirectional flow, the only terms that survive here are the one component that's not zero, right? So I can just immediately write this as Vx d dx Vx, right? Because if I try to write anything else, a y or a z in any other direction, they're all zero. But I just showed from the continuity equation that dvx dx is 0. So this term is also 0. Okay? And maybe to rationalize that, think about this for a minute, or what this is saying. V dot grad V equals 0. This says that velocities are normal to the velocity gradients. That's what that means, right? I'm saying that the dot product, the velocity in that direction, right? And then I say the gradient of the velocity, okay? They have to be at right angles of each other. So that's implied by saying our unidirectional flow. That's not obvious, but that's what it says. Okay? So using this, we can simplify the Navier-Stokes equation. And I'm going to skip the derivation, but for Cartesian coordinates, this ends up being rho dvx dt is equal to minus dp dx. That's how I want to make curly p, I think. Curly p plus mu d squared vx dy squared plus d squared vx dz squared. Okay? And I also get that dp dy equals 0 and dp dz equals 0. Okay, so the Navier-Stokes equation simplifies to this. And often what we're going to find is we're going to solve these two-dimensional problems. So in a two-dimensional problem, we often say only care about what's happening in the y or the z direction. So suppose we can do this without a loss of generality. Suppose that we just say then that Vx is not a function of z. Okay? In that case, now we're just going to get this guy, and that guy. Okay? And we also often have steady problems. Okay? That would mean dvx dt equals 0. Okay? So these are the kind of like undergrad problems that you get. They end up being one-dimensional, right? You can turn them into ODEs. This is all the problems that you end up doing with shell balancing end up being these kinds of problems. Okay? So we're out of time. So I'll do a couple quick examples of these next time before we dive into the energy equation. Okay? And you have some of these on your homework. But almost all of them will reduce to these unidirectional flow problems. Okay? These problems here, they'll take PDEs to solve. Okay? they're easier than the full Navier-Stokes equation, which is impossible to do, at least as far as we know. But these two guys will be able to take PDE, methods and solve them and do something with it. Okay, so the rest of the chapter and all before the exam, there are these kind of problems. After the exam, we'll dive into methods of how to do this. Okay.
Thank you.